In particular, the conservation of angular momentum, which runs as follows. So let me remind you of Newton's second law for rotations. In the form that I had worked it out last time or the time before, it says that the total external torque acting on a system, internal torques don't count, total external torque acting on the system is the rate of change of the total angular momentum in particular. If there is no external torque acting on the system, then the total angular momentum is a constant in time derivative is zero, or as we say, the angular momentum is conserved. That's the law of conservation of angular momentum. Remember, it applies only when there's no external torque or no net external torque acting on the system, so it's not absolutely universal. But if there's no external torque acting, then the angular momentum is conserved. This law happens to be very powerful. It's analogous to the law of conservation of momentum, which is very powerful for dealing with collision problems and whatnot. The law of conservation of angular momentum lends itself to a whole variety of different situations, including some really weird ones, and it also allows for some wonderful demonstrations. So today we get to play with toys. Examples. One. Maybe the classic example is the ice skater. Why ice? Ice skater is doing one of those twirl things. So here she or he is, but she's got her arms outstretched like that, and she's spinning around, but not too fast. Then she brings her arms in close to her body. Until I practice this drawing. Brings her arms in close to her body. So originally she was spinning around like this, but not too fast. Brings her arms in close to her body, spins much faster. So, why is that? Well, when she had her arms outstretched, she had a relatively large moment of inertia. I was large. When she brings her arms in close to her body, what is she doing? Basically decreasing her moment of inertia. Angular momentum is the product of, for a rigid object, I times omega. Of course, she was not rigid actually while she was bringing her arms in, but she was rigid in the first instance, so she had some moment of inertia then, and she's rigid again when she got her arms down close to her body, so that she's again a rigid object. So at the two extremes of this case, that formula applies. L is equal to I times omega. What she has done is to decrease her moment of inertia, because angular momentum is conserved, the omega must go up in direct proportion. Make sense? I need a volunteer, an ice skater. Step right up. You look like an experienced ice skater. To make the effect a little more dramatic, we're going to give her some weights here. So that bringing her arms in, she's actually changing her moment of inertia a whole lot instead of just a little bit. Step on the platform, if you please.
She's gonna hit the rule, you're going too fly.
Hit the rope.
Yeah.
Let's get this rope out of here. Okay. Arms out, please. Whoop. You're losing your balance. When you have ballet lessons, look at the clocks and concentrate on the clock.
Turn your head.
Okay. Bring your arms in. Stretch them out if you're getting dizzy. They want a repeat performance. That was too good.
We love you, Peru.
And when you get going too fast, pull your arms out again, and that will slow you down. Okay. Very good. So there's the law of conservation of angular momentum in action. A second example. I got a bicycle wheel here, and let's say that it's held about a vertical axis like this, and it's spinning. Now it happens that there's a mouse. I didn't bring the mouse. There's a mouse at the center, and it crawls out one of the spokes. As it crawls out one of the spokes, this is supposed to be frictionless, it obviously isn't, but as it crawls out one of the spokes, what happens to the spin of the wheel? Goes faster? Goes slower. Why? Because the moment of inertia of the whole system, wheel plus mouse, is getting bigger and bigger as the mouse gets further and further out, mr squared. So the moment of inertia gets bigger, so the angular velocity has to get smaller. Same story, only sort of in backward way. So let me draw that case. Here's the bicycle wheel. And let's say its initial angular velocity is omega, and it's got a mass m. So here it is, omega, and then the mouse, whoops, wheel, sorry. Mouse, there's the mouse, and he walks out. And then at the end of the process, the mouse is out here on the rim of the wheel, and the mouse, he's got mass m, and the radius of the wheel is r, and because it's a wheel, what's the moment of inertia of a wheel? Essentially. It's basically a hoop. The reason I like the bicycle wheel here is that basically all of the mass is out at the rim. There's a little bit here that's on the axis, but let's pretend that all of the mass is out on the rim, and the spokes don't weigh anything. So it's just a hoop, and therefore the moment of inertia is simple. The original angular momentum was I original times omega initial. The original moment of inertia was nothing but mr squared. The final angular momentum with the mouse out at the rim is equal to I final times omega final, but I final is the moment of inertia of the bicycle wheel, still mr squared, plus the moment of inertia of the mouse out there. What's the mouse's contribution to the moment of inertia? Just mr squared. So the mass of the mouse times r squared, that times omega final. I set those two equal to each other. There's conservation of angular momentum, no torque, anything to slow this thing down or speed it up. So mr squared omega I is equal to m plus little m times r squared omega final. The r squared cancel, and I get omega final is equal to m over m plus little m, whoops, times omega initial. So there's a typical problem in conservation of angular momentum. Mouse walks out the spoke. wheel slows down. Why? Angular momentum is conserved. If the moment of inertia went up, the angular velocity's got to go down. Proportion. Okay, let me show you a more subtle, much more subtle problem in conservation of angular momentum. There are 1,000 of this generic type, like an ice skater and a mouse on a wheel and so on. But let me show you a more, as I say, a little bit more sophisticated example. Imagine that you're at an ice rink or something, and here is a stick. Somebody's broken hockey stick is lying on there on the ice, and it has a lump of clay, mass M, attached to one end. And for the moment, I'm going to pretend that that hockey stick is massless. Now another lump of clay. Make it a hockey puck if you want to, but I don't know how to make the hockey puck stick out to the far end of that stick, so I'm thinking of a lump of clay, something or other that will grab on when it comes there. So this is going along like this with a speed v0, and it's also got a mass m, and let's give this stick some length. Let's say it's length L there. And the new lump of clay comes along and sticks onto the far end of this stick. The whole system is frictionless. So what's going to happen afterwards? Well, the whole system is going to be moving on to the right, isn't that right? And moreover, it's now going to be rotating too. So I've got rotation and translational motion in the system. Here is a scene beforehand. And the scene afterwards is that the thing is kind of tumbling. This is all viewed from above. Of course, we're looking down on the ice rink. There's this hockey stick lying flat on the rink, and mass M on one end. Another mass comes along, sticks onto that end, and the thing flies off, slides off, tumbling, rotating as it goes. So it's rotating with angular velocity omega, and it's also moving with the center of mass of it is moving with velocity v. So there's the situation afterward. I don't know how to describe this, except maybe I can do it with this. Here, there's a lump on this end, another lump comes along, and the stick was originally at rest, right? The other lump comes along and hits this, and now the thing is sort of tumbling. The thing is going along like this, rotating and moving. And I want to know what's the final velocity and what's the final angular velocity. Well, conservation of angular momentum says conservation of angular momentum about what point? What would a sensible point be to use for this system? I think I'm going to use the center of the stick as my point about which I calculate angular momentum. What was the angular momentum originally when this thing was just coming along, stick and mass attached or not moving? You just got a mass flying along like that. I want to know the angular momentum about a point off the line of the trajectory. Do you happen to remember the formula? I did this as an example at the beginning of angular momentum. Is something that's going in a straight line at constant speed. What is its angular momentum? Anybody remember it? We can get it from L equals R cross P. That's R is this distance here right at the moment. And so it's R times mv times the cosine, not the cosine, the sine of the angle between the two. Sine of the angle between V and R. That's this angle here. And therefore, if I combine the R with the sine theta, what is R r times sine of theta is just this distance here, the far end of this triangle. That's L over 2 in this instance. So the rule that I'm trying to remember is it's mv times, let's call it b, the point, the distance of closest approach from the trajectory to the point. In this case, L over 2. So the angular momentum of that thing as it was moving along before it hit was Li equals mv0 times L over 2. In general, mv times what I'm trying to avoid saying the lever arm, because to me lever arm conjures up the notion of torque, and it is, I'm not talking about torque, I'm talking about angular momentum, but it's the same idea. Extend the line along which the motion is taking place, extend the trajectory along here, and then the distance of closest approach is mv times the distance of closest approach. Okay, that's the initial angular momentum. What is the final angular momentum when this thing is rotating around? Well, it's I times omega final, and I, moment of inertia for this dumbbell, about the center of the dumbbell, is 2, because there are 2 ends, m, the mass of each m, times the square of the distance away that that mass is, that's L over 2 quantity squared. So that's the moment of inertia, 2 L over 2 quantity squared, that times omega. That's the angular momentum after the collision. So what does this tell us? If I look at this equation and this equation here, mv0 times L over 2 equals 2m omega times L over 2 quantity squared. Well, one of these L over 2's cancels with that one. The 2 cancels here, the m cancels, and I get omega is equal to v0 over L. Omega is equal to v0 over L. That's the angular velocity of this thing as it spins away. How about v? I haven't figured out what the velocity of that is. Any idea about how I can calculate the velocity of this? The velocity of the center of mass, actually, of this system after the collision?
Conservation of energy?
Not conservation of energy. This is a sticky collision, and energy is going to have been converted into heat in this process. So kinetic energy is not going to be conserved, but you're close. Try again. How about conservation of translational momentum? This was conservation of angular momentum. This is a collision process. So conservation of translational momentum. Remembering that the center of mass of the system, which I cleverly chose to be the point about which I'm calculating the angular momentum, the center of mass moves just as though all of the mass was concentrated there. Okay, center, the conservation of translational momentum. So what was the momentum in the original situation? Just mv0, huh? And the momentum in the final situation? The momentum of the center of mass? It's as though I had 2m concentrated in the center, so it's 2m times v, and that tells me that v is v0 over 2. How about that? So this thing is moving along at half the velocity. The center of it is moving along now at half the velocity that this lump came in with, and meanwhile it's rotating with an angular velocity that's that initial velocity over L. Question for you. How fast is the top mass moving immediately after the collision? It's moving, actually, the top mass is moving to the right for 2 reasons. First of all, because the whole damn thing is moving to the right at center speed v, and secondly, because it's also rotating. So what's the net velocity of that topmost point immediately after the collision? Of course, long after the collision, it's complicated. That thing is moving in some kind of weird, cycloidal motion. But immediately after the collision, how fast is it going? top in the diagram. Of course, this is all happening on a horizontal plane, but how fast is the top mass going? Well, the velocity, let's call it, of the top mass is the velocity of the whole center of mass. It partakes in that motion, v plus the velocity that would have had just due to the rotational motion. What's that? That's going to be omega times L over 2. Omega times r in general, the velocity because of the rotation. Okay, let's put in what the numbers are. V was, we found V0 over 2. And omega was, we found V0 over L times L over 2 now. The L's actually cancel. I get V0 over 2 plus V0 over 2. V0. How about that? Immediately after the collision, that topmost mass is going the same speed that it was before the collision. Yes?
Do they have the same direction? V and omega times L over 2?
Yes,
So we
at
have
that very moment, just when it's stuck on there, like this, just after the collision. So it's going purely to the right.
Oh, okay.
A little while later, when this thing is tilted over, it's true, it's going at a weird, slight sloping down. But right after the collision, that's all I'm asking. Right after the collision, how fast is it going? Answer, it turns out exactly the same speed it was going just before the collision. Does that seem reasonable? I think it's reasonable, but I don't think it's obvious. And in fact, in a moment, I'll make it even less obvious than that. By the way, what's the speed of the bottommost point immediately after the collision? How would you calculate that? Well, it's going to the right because of the motion of the whole center of the whole thing with a speed v. But meanwhile, because of the rotation, it's actually at that moment going to the left. How much? Exactly the same amount. The bottom one would be Vb is equal to V minus omega L over 2. Did I do that right? Yes, because it's going to the right because of the translational motion, but it's going to the left because of the rotational motion, and those exactly cancel out. It's the same reason that they conspired down there, so this is V0 over 2 minus V0 over 2 equals 0. That bottommost one is instantaneously at rest. Seem reasonable? Now, I thought of doing this, but I think I will not, but I'll leave it for you. You know, you have all the information to do this now. Try doing the same calculation with a stick that's not massless. If you gave the stick some mass, capital M, for example, then that would change the details here because there's some extra mass in the problem, some extra contribution of moment of inertia. In that case, if you gave the stick some mass, it would still be the case, of course, that it moves off and it's rotating, but the actual amount of the rotation and the linear motion would not be the same as it is here. And in fact, you would find that it's no longer the case that the bottommost point is immediately at rest and the topmost point just keeps going with its original velocity. The topmost point is moving somewhat slower than that, and the bottommost point is actually moving in the backward direction a little bit immediately as it starts. In fact, it's a fun problem to calculate. In that case, what point on the stick is instantaneously at rest? It's not the very bottommost point. It's some point a little way up, and you can calculate exactly how far up it is. I sometimes think of this as, suppose that you were taking a picture of this process and you had a kind of lousy camera that wasn't very fast, didn't take very fast exposure. What would you see? In the case that I did here, you would see that the bottommost, in the photograph right after the collision, the bottommost mass would be nice and clear and sharp. The top one would be really fuzzy because it was moving while the picture was taken. If you did it with a massive rod here, you would find that the bottom one is sort of fuzzy, the top one is really fuzzy, but that there's some point right at sort of partway down in the stick that's absolutely crystal clear, because that's the point. It's called the center of percussion, that at that very moment is not moving. For those of you who played pool, by the way, I don't know if you ever thought about this, but you know that the height of the cushion, where the billiard ball hits the cushion there, there's no accident what that height is. You've got to build your billiard table with that height exactly the right ratio to the radius of the billiard ball, or else the balls will not bounce nicely off the edge. In fact, I think it is that it's 7/5 the radius is the height here, as I remember, as it comes from the moment of inertia of the sphere. But you want that height to be exactly such that the point of contact where it hits there is the center of percussion for this, the point which would instantaneously be at rest. If you put this thing too low, then when the ball hits it, it slips on there, and that makes for a not perfect bounce off the edge. Check it out next time you're in a pool room. Measure the height of that thing and the radius of the billiard ball, and I believe you'll find that it's 7/5 the radius. Not bad. Anyhow, let's do another demonstration here. I need another victim. Okay, other end of the room. You, sir. He step right up. You will hold the sweep. Line this up. This is not so dangerous, actually. At Reed, we have one of a bicycle wheel like this that's loaded with lead weights around the edge, so it has a huge moment of inertia. This is just a hunk of solid rubber. So listen, I'm going to pull this thing. You better get a little further. Well, maybe I should tell you what you're going to do. Once it's spinning, you're going to stand on there, and then when I instruct you to, you're going to rotate it into the vertical plane, and then turn it all the way upside down. Make sense? Exactly. Only it's going to be spinning. It's going to feel really weird, believe me. Right? Hold on tight. Whoops. Perfect. Everybody see that? Go, Chris, go. Back the other. Slow it down a bit. Very good. I think they got the idea. Stop. Stop. I'll leave this around after the lecture. It's the most bizarre sensation. I knew a guy once who made a demonstration. He had a wheel like this that he put into a suitcase. And then he would come into the class carrying the suitcase, and then he tried to stick the suitcase onto the table, and it flies up. Did you see that? I'm carrying the suitcase, and now I want to put it up sideways on the table. What happened there? This is example 4, and we had a rotating cable here. Person standing on it, holding bicycle wheel, rotating like that. Turn the bicycle wheel upside down. And you start rotating the other direction. Actually, you started rotating even when you first got on there. So I guess you were probably not holding it exactly vertical or something like that. So, what ideally you would have seen is that he was standing on here, holding it in a horizontal plane and wasn't rotating at all. Then he turns it this way. Suddenly the wheel. Then he turns it this way. So what's going on here? Of course, the bicycle wheel, when it's spinning like that, has a big angular momentum in that direction. Turn it upside down, it's now got an angular momentum of the same magnitude, but now pointing down. Somebody's got to soak up that angular momentum, and you kindly did it. You rotated it. In fact, your angular momentum was actually twice the angular momentum that the wheel itself had, right? Because when you turned it over, you converted it from L pointing down to L pointing up. The total change in angular momentum of the wheel was 2L, and you soaked up the difference. Now, as long as we've got the toy here, I want to show you the most bizarre of all phenomena involving angular momentum. This is not going to be conservation of angular momentum, but because it will actually be a torque acting, I have in mind the gyroscope. So I need another assistant. We're back to this side. Don't worry, this one's not dangerous. All you have to do is hold the wheel while we get it going. Actually, let's get this thing out. We're going to just spin the wheel up and then hang it from that string. In fact, as soon as we got it going, you can hand it to me, okay? You want to, let's start with you over here before. Face me. Okay. No, you need to hold both sides. Right. All you're here for is to hold it. Wow, it's a bit tough. Are you ready? Hold on tight. Stick around, I'm going to need some help hooking this thing on. Yeah. Okay. Ready?
Let's see it.
Here goes.
It's possessed.
Actually, this is cute. It's showing up. Can you guys see? Stand around a little bit. Don't worry about the bouncing. I'll tell you what that's doing in a moment. But
Run away. It's losing speed.
it's losing speed, yeah. Notice something as it loses speed because of friction. Is the precession actually speeds up. It's losing the effect now. We call this precession when the thing rotates around like that. Okay, thank you. Why does that happen? Personally, I think when I first saw this, I couldn't believe my eyes because it looks like it defies gravity, right? If the thing wasn't spinning and I let it go, of course it just flops down. Naturally, gravity is pulling it down. But if it's spinning, that's not what happens at all. It rotates around like this. It doesn't flop down. Why is that? try to draw a careful picture of this thing. Here's the ceiling. Here's the rope coming down from the ceiling to the point here where the hook is. And then there's the axle of this wheel, which I'll draw a little bit longer than it actually is, just so that we can see the situation. That's the point about which I will calculate torques and angular momentum. Here's the wheel now. And it's spinning like that. That doing it? Very well. So I got the bicycle wheel here, and it's spinning around. It's supposed to be coming out of the board and into the board here, and it's spinning in that sense there. What direction is the angular momentum of the wheel? It's spinning like that. Grab it with your right hand, fingers indicating the direction of the spin. Then the angular momentum is pointing to the left. What's the R in this problem? From the point about which I'm calculating torques to the place where the force acts. What force is acting on this problem? Damn, I meant to say that at the beginning. What's the force acting? Gravity, huh? So gravity is acting straight down here. This is not a case of conservation of angular momentum. By the way, there is an external torque acting on this system, namely gravity. Now, let's see. Do I have all the ingredients in there? Here's the point about which I'm going to calculate torques. Here's the place where the force acts at the center of the wheel. The force is mg, pointing straight down. The angular momentum of the spinning wheel is to the left. What direction is the torque about P? Torque about P would be R cross F. That's R crossed into F. Put your fingers in the direction of R. Cross them into the direction of F. Your thumb indicates the direction of the torque. The torque is coming straight out of the board in this case. Right? Let's see if I can draw that. So the torque comes straight out of the board. Why doesn't this wheel flop down? If it were not spinning, it certainly would flop down. And we could explain that by saying, well, the torque is out of the board, so it's going to produce some angular momentum. The angular momentum has got to be pointing out of the board. How could I do this with this wheel? Have it move down in that direction. I would produce some angular momentum that's pointing downward. But this thing doesn't move that way. That's because it's already spinning. It's already got that angular momentum to the left. Torque produces a change in angular momentum. So this tells me that a change in angular momentum points out of the board. Let's look at the system from above. So I'm going to look down on this thing now, and I see L pointing like this. But there's a torque which is pointing out of the board. So that means the change in L has got to be in the same direction as the torque. Here in the next split second is the change in the angular momentum. Looks like that. So that the thing has now processed actually through an angle, let's call it theta, viewed from above. So instead of pointing in that direction, it's now pointing slightly out of the board. This thing has now rotated into this position, and it's going to rotate all the way around. That's precession. And what I like to do is calculate what's the angular velocity of the precession. You understand what I'm talking about, the precession? That's the motion that you saw here. It was spinning. There are two kinds of angular motion that's going on here. First, there was the spinning of the wheel, and then there was the precession, that the whole wheel moves slowly around. That's precession, and I want to calculate the angular velocity of that. So here goes. The angular momentum, which was originally pointing directly to the left, is now pointing slightly out of the board, viewed from above, in the same direction that the torque points. So the angle there, d theta, is equal to, by ordinary radian measure, is the length of the arc, dl over L. But L is equal to the angular momentum of the wheel. The original angular momentum of the wheel is I times omega. That's the moment of inertia of the wheel, mr squared. That's the angular velocity provided by u, or u, I guess, when we spun the thing up. That's the angular velocity of the spinning of the wheel. And dl, what's that? That's the change in the angular momentum. That would be tau, the torque, times dt. Isn't that right? dl by dt, rate of change of angular momentum, is the torque. What is the torque in this instance? Force times lever arm. Force is mg. Lever arm is r. By the way, what's r on this actual wheel? It would be the distance from the place where I hooked it on to the center of the wheel. So it's about 8 centimeters here, from there up to here is the r in question. So the torque is mgr, and the change in the angular momentum is mgr dt. Stick that into my original equation, and I have d theta is equal to dl, that's mgr dt, divided by L, which is I omega. And that tells me then what the rate of change of the angle is. d of theta over dt, d theta by dt is mgr over I omega. This is the precessional angular velocity. We call it capital omega. It's the angular velocity of the precessional motion. The rate of change of that angle, the angle that the angular momentum makes with some fixed axis.
What do you call it? Cap what?
Omega.
No, but what does the cap mean? Capital omega? Oh,
Capital.
capital, okay.
Uppercase omega. On a campus with lots of fraternities, you should know what that stands for. Or if you're an electrical engineer, because it's a symbol for an ohm. So, angular velocity well, I can calculate the angular velocity of precession, but it still doesn't satisfy me. Why does this system work? Why does it defy gravity like that? Instead of flopping down, it rotates around. This is the angular velocity at which it precesses. By the way, notice that as friction slows the wheel down, the spinning down, omega gets small, little omega gets smaller. What happens to capital omega? Actually gets bigger. So the precession rate gets faster and faster as this thing, as the spinning rate gets slower and slower. Very strange. Let me tell you an analogy. The gyroscope is actually very closely analogous to planetary motion or circular motion in general. I could raise all the same paradoxical questions about planetary motion. Here's the sun, and here's the planet going around it. What's the direction of the force? In toward the center. How come the planet doesn't fall in toward the center? Well, it would, except that it happens already to be moving. It's got some momentum along like this. So the change in momentum between one instant and the next, the change in momentum really is in toward the center. But that doesn't have the effect of making the planet fall into it toward the center. It has the effect, since it was already moving like this, of changing the direction of its motion, of pulling it around in circular motion. Same story with the gyroscope. The torque is pointing out of the board. Why doesn't that make the damn thing flop down? Gravity is trying to pull it down. Why doesn't it go straight down? Well, it would have if it had not already been spinning. But it already has some angular momentum due to the spin in this direction. So the torque instead has the effect of changing the direction of that angular momentum. Instead of making it flop down, it changes the direction of its angular momentum, so it's now pointing slightly out of the board. And then, of course, in the next instant, a little bit more, and so on. And it spins or processes around like this. Of course, small fraud in this. Not a fraud, but a condition, an unstated condition. That planet goes in nice circular orbit only if I started out with exactly the right velocity given its radius, right? If you had a planet that was going in a nice circular orbit and you spanked it, what would happen? Suppose it is going around like this and an asteroid hits it from behind or something like that. What happens to that orbit? Do you happen to know? We never analyzed non-circular motion, but it would knock it into an elliptical orbit. Likewise here, I have to actually start the precession with exactly the right precessional angular velocity, or else it will start to fall down, and that's what causes the second effect that you notice there, nutation. If you don't have the precessional angular velocity exactly right, or if you spank the thing, it will nutate, which means that it bounces up and down as it goes around. Three kinds of rotations here. Spinning on its axis, precession around in the circle, given by his theory, and nutation, if it doesn't have exactly the right angular velocity to go around smoothly in a circle. Hey, there will be a lecture on Wednesday, but it will be a rather different topic. I'm going to talk about statics on Wednesday.